walk past one of those massive regeneration projects and just wonder what's going on behind the hoardings.
Yeah, especially down by the water.
Exactly. We're looking today at Rochester Riverside in Kent. It's this huge 32-hectare site right on the River Medway.
Big project.
Massive. It used to be really industrial for almost 200 years. Old gasworks, that sort of thing. Now they're turning it into housing maybe 2,000 home shops, a whole new waterfront stretching 2.5 kilometers.
And that history, the industrial past, that immediately throws up challenges, doesn't it? Contamination, old structures.
Right, especially along the river edge itself. It was apparently a real patchwork. Old wharves, crumbling walls, bits of sheet piling.
All needing replacement, basically. And you've got to provide flood protection for this new development, too.
So it's this complex puzzle. Renew the area, deal with the contamination, and build a completely new river frontage.
A huge part of the job. Which brings us to the solution they picked for that crucial river wall element.
Steel sheet piles.
Yeah, exactly. Hot-rolled steel sheet piles. They looked at various options, obviously, technical performance, cost, environment, safety, all the usual factors.
And steel came out on top.
Yeah, it was seen as the best technical fit and, crucially, the most cost-effective approach for the specific site.
And we're not just talking a small section here.
Oh, no. We're talking virtually the entire 2.5 kilometers.
Yeah.
The main river frontage, the creeks, the wharves, all secured by this continuous steel wall.
How deep do they have to go?
Roughly 15 meters deep on average, then topped off with a concrete capping beam to tie it all together. The scale is just, well, it's significant.
And the steel itself, you mentioned ArcelorMittal supplied it.
That's right. Over 4,200 tons in total. And they use specific types, the AZ sections, AZ12, AZ14, right up to AZ28 in some places.
Different sizes for different needs.
Precisely. It's about optimizing the design, using the right strength where you need it. They particularly favored the wider AZ sections.
Okay, why those?
Well, a few reasons. They offered a really good balance between strength and cost, which is always key on big projects.
Sure.
But also, wider piles mean fewer piles to install overall and fewer joints between them. So that speeds up installation.
Ah, makes sense. Quicker work.
And it also potentially increases the water tightness of the finished wall. Fewer gaps.
Okay. And were they thinking long-term durability as well?
Definitely. The design of those EZ sections, the way the thickness is distributed, helps with longevity. Plus, and this is important, they came with a special glass flake epoxy coating.
Applied before they even arrived.
Yeah, applied at the mill. So it's like factory-applied protection against corrosion right from the start. Gives it a much longer design life.
So how do you actually get, 15-meter-long steel sections into the ground, especially 4,200 tons of them?
Primarily using powerful vibratory drivers. These machines essentially vibrate the piles down into the soil.
Like a giant tuning fork pushing them in.
Sort of, yeah. For some areas, like the creeks, they used crane-suspended drivers with these long leader rigs, about 18 meters, to guide the piles accurately.
And they managed to get a decent pace going.
Oh yeah, pretty impressive rates. Along the main frontages, driving panels of piles, they were hitting around 40 linear meters of wall per week.
40 meters a week.
And on some of the landward sections or creek walls, it was even faster, sometimes over 100 linear meters a week.
That's really shifting some steel.
Yeah.
I also saw they used a high-strength steel grade S430 GP. What's the benefit there?
It just gives you an extra safety margin. If you hit unexpectedly tough driving conditions, a buried obstruction maybe.
Right, like hitting a rock you didn't know was there.
Exactly.
Right.
That higher strength gives you a bit more robustness. And it also contributes to the overall long-term durability of the structure.
Now, you mentioned challenges earlier. Contamination, old structures. What else do they have to contend with? It's never straightforward, is it?
Never on a site like this. The tides, obviously, working by the river, means constantly factoring in the water levels.
That must complicate things.
It does. Then the contamination that needed remediation, they actually dredged about 400,000 cubic meters of sand from the Thames estuary to raise the site levels, and then treated the contaminated soil on site using bioremediation.
Wow, quite the process.
And yeah, those unforeseen obstructions during piling are always a possibility. Plus, to help the new ground settle properly after raising the levels, they installed things called vertical band drains.
Okay, what do they do?
They basically help squeeze the water out of the soil faster, accelerating the ground settlement so they could build sooner.
So many interconnected parts. Even just getting the steel there must have been a job in itself.
Huge logistical exercise. The piles came by ship from Luxembourg, from the inland port at Murder, all the way to Rochester.
Just in time.
Yeah, phased deliveries over nearly 6 months to match the construction program. They had to be really careful handling them too, using special vessels and lifting gear with a big Cobeco crane, specifically to avoid damaging that protective coating.
Right, you don't want to scratch the raincoat.
Precisely.
And with new buildings planned right near this wall, they needed robust support systems behind it too, I guess.
Absolutely. Because the wall is retaining quite a height difference in places and supporting the land for the new buildings. They used a variety of techniques depending on the location.
Such as?
Well, in some areas, they reused existing concrete anchor piles that were part of older structures, adding relieving platforms.
Yep.
Elsewhere, they installed new angled A-frame concrete piles or ground anchors drilled deep into the soil.
Okay.
Also angled steel tubular piles, and in some spots even double walls of sheet piles tied together, with the space between filled to create a really sturdy gravity structure.
Lots of different engineering solutions there.
Yeah, and sometimes where an old structure was just left in place, they'd drive the new sheet piles right in front and just fill the gap behind with crushed concrete. Whatever worked best for that specific section.
It really sounds like these steel sheet piles, the ArcelorMittal ones, were absolutely fundamental to making Rochester Riverside happen.
Oh, undeniably. It was the core solution for that critical river edge. The way they integrated the steel piling with all the other remediation and construction work, it's a great example of tackling complex challenges effectively. It really stands out as a sort of a reference for good performance on this kind of waterfront project.
It really does. And considering that scale, the 4,200 tons of steel, the 15-meter depths, all those support systems, it makes you think, doesn't it? What other huge, almost invisible engineering solutions are underpinning the developments and infrastructure we see every day?
That's a good question. They're often hidden, but absolutely vital.
Definitely something to ponder next time you're out and about.